Hi, welcome back. We're on Chapter 9, Mr. Cavendish and Inflammable Air. Unlike Presley, Mr. Cavendish was quite rich. You would not know if you saw him. He always wore the same tattered and stained clothes, an unfashionably old hat. He never had time for the truffles of fine clothes and fashion. Mr. Cavendish was utterly absorbed in chemistry. He performed many carefully and important experiments, but remember him for first identifying hydrogen and showing that water is made of hydrogen and oxygen, although he the air oops, would have said that the air which he thought might be phlogiston was dephlogisticated air. In a famous experiment, Cavendish poured what we now know to be dilute sulphuric acid, first on zinc, then on iron, and finally on tin. Using the same method as Presley, he trapped the gas emitted each time. Then he did the same thing again, this time pouring spirit of salt, or hydrochloric acid, HCl as we now call it, on the three metals, and again he carefully trapped the gas emitted each time. He touched a lit taper to each of the 6 samples of gas, and all burned with the same pale blue flame. It was the very same gas. Since this gas could be lit, he called it inflammable gas. That is, gas which is able to burn. He thought this inflammable gas came from the metals zinc, iron, and tin, and since it burned, he wondered if he might have released the phlogiston trapped in the metals. Remember, the phlogistians thought that when metal was heated, it released phlogiston. So Cavendish reasoned that this gas might be phlogiston contained in the metal, but he was not quite sure, and generally called the gas inflammable air. What actually happened? If we look at the chemical formula above, H2SO4, which is sulfuric acid, and HCl, which is hydrochloric acid, we can see oops, we can see to use 2 examples that shall make it clear for all 6. When the dilute sulfuric acid was poured on iron, the iron traded places with the hydrogen, and the hydrogen was then released. If we look at modern symbolic representation of the reaction, it will be quite clear. Iron plus sulfuric acid equals iron sulfate and hydrogen. Hydrochloric acid poured on iron released hydrogen in the same way. This time the iron switched places with the hydrogen to make an ion chloride and hydrogen. Iron plus hydrochloric acid equals iron chloride plus hydrogen. We can see that what Cavendish thought might be phlogiston was actually hydrogen. Yet even with this confusion, it was an amazing and important discovery. But he did something else even more amazing and important. He put dephlogisticated air oxygen and phlogiston or inflammable air hydrogen into a glass globe and sparked it with an electric current. It exploded and he found water. Water formed on the inside of the glass globe. Oddly enough, others had done the same experiment, but it did not strike them that 2 gases could make water. And they do. And furthermore, Cavendish found that if 2 volumes of inflammable air hydrogen were sparked with 1 volume of dephlogisticated air oxygen, all of both gases turn into water. This was an amazing discovery, much, much more amazing than Cavendish, Presley, or anyone else could have known at the time. 2 volumes of hydrogen combined with 1 volume of oxygen to make a very much smaller amount of water. Cavendish had discovered the very famous chemical formula for water, H2O, almost. You see, Master Cavendish saw the whole thing as a phlogiston. He thought that the inflammable air hydrogen was actually water plus phlogiston, and the phlogisticated air, oxygen was actually water minus phlogiston. What happened when you add water plus phlogiston to water minus phlogiston? The plus and minus phlogistons cancel each other out, and you are left with only water. Okay, you can see Mr. Cavendish was still thinking of water as an element, and it wasn't until someone realized that water was actually made of two distinct gases that the notion that water was an element could finally be rejected. Both Presley and Cavendish knew someone, a Frenchman, who insisted that there was no such thing as phlogiston, and hence no such thing as dephlogisticated air. The French scientist invented the names hydrogen and oxygen. He argued that Presley and Cavendish, brilliant as they were, had gotten things exactly backwards and set out to make it right. The Frenchman was Antoine Laurent Lavoisier. Presley would not listen to this dying day when most chemists called Lavoisier that it was still holding fast to the nearly dead theory of phlogiston. I feel perfectly confident of the ground I stand upon, he declared. Truth will in time prevail over any error. Cavendish simply shrugged his shoulders and remained a lukewarm believer of phlogiston. Truth did prevail, but it was Lavoisier who was right, as we shall soon see. Chapter 10. Chemistry's French Revolution. Antoine Laurent Lavoisier was a scientific revolutionary born in the midst of political revolution. He found both his country and chemistry in a state of confusion, and both in serious need of reorganization and repair, and he worked with great diligence and intelligence to help both France and science. Sadly, the revolution in France cut short the life of this great revolutionary of science, but before he climbed the scaffold to the guillotine on the 8th of May in 1794, he had already completely redefined chemistry, turning the backwards forwards and putting the upside down right side up. Lavoisier was the son of a rich lawyer and defender of the King of France. But things were bad in France in the last half of the 1700s. The poor paid too many taxes and had too little food. The rich seemed not to care about the sad lives of the far more numerous poor. Louis XVI, the King of France, was neither strong enough nor clever enough leader to avoid the coming thunderstorm of revolution. In 1789, the storm broke, and the entire order of France was turned upside down. The French Revolution had begun. But that very sad year Lavoisier published his elementary treatise on chemistry, and that turned the science of chemistry right side up. Lavoisier did not begin as a chemist, however. He first studied to be a lawyer, just like his father, but someone persuaded him to sit in on a very popular chemistry course, and young Lavoisier never thought of becoming a lawyer again. He very soon decided that he wanted to become a member of the prestigious French Academy of Science, and once Lavoisier decided something, it was already halfway to being accomplished. When he was just over 20 years old, he entered a competition sponsored by the Academy of Sciences, Find an economical way to light the streets of Paris. They commanded the competitors. Lavoisier spent long, hard hours on the problem. For his suggestion, King Louis XV ordered the young Lavoisier be given a gold medal. All his life he did many things for his country and for kings. He found French gunpowder to be the most poorly made in Europe. Under his direction it became the best. He tried to bring about a better supply of water to Paris, and advocated the use of fire hydrants as well. He called for reforms of the prisons, and for the government to pay for life insurance for the poor. He tried to help the farmers by showing them better methods of cultivating their land. He did all these things and more for his beloved France. But his greatest achievement was the reform of chemistry, something he did not only for France, but for the whole world. Some historians of science think Lavoisier did not discover anything new. They argue that he merely took the pieces of the chemical puzzle that various scientists had already been puzzling over and showed them how they really fit. Others think that Lavoisier did indeed discover many things, very important things. Who is right? Well, it's difficult to say. Read on and see what you think. Everyone agrees that Lavoisier was the first to see that phlogistians had everything backwards. In October of 1774, he happened to meet Mr. Priestley in Paris. At dinner, Priestley described his creations of dephlogisticated air by heating calx of mercury. Lavoisier sat wide up and drank in everything Priestley said about the strange pure air that made candles dazzling bright. He had to repeat these experiments in his own laboratory immediately. He returned to his laboratory, cooked and measured, and scratched his head. He heated and boiled and weighed and paced up and down. Something was very right with Mr. Priestley's experiment, but very wrong in Mr. Priestley's interpretation. And then, voila, it all fell in place. Voila is French for behold or see there. Lavoisier set up an experiment to see whether his suspicions were correct. He suspected that the air, or something in the air, was going into the mercury and making it calx. Lavoisier put 4 ounces of mercury into a glass retort, a French vessel version of the alembic. Lavoisier's retort had a very long neck and stretched up from the vessel bulb, then down and back up again like a letter J. The hook on the J went under another glass jar shaped like a bell. This bell jar was then to be used like Mr. Priestley's pneumatic trough, but with 2 very important differences. First, instead of trapping gas in the bell jar, Lavoisier was trying to see if the air was removed from the bell jar, drawn back into the J tube and into the mercury. Secondly, to measure how much air was removed, Lavoisier did not fill the bell jar full of liquid. He used mercury, but filled it with just enough mercury so that 50 cubic inches of air would remain in the bell jar when he turned upside down in a tank of mercury. Here is Lavoisier's device. Okay, Lavoisier went to work. He heated the mercury for 1 day. Nothing happened. But the second day, the specks started to appear in the mercury. Calx of mercury he heated and heated for a total of 12 days, and no more red specks appeared. The air in the container, it had contracted from 50 cubic inches to 42 cubic inches. See there, he cried. Lavoisier had proven that the phlogistians had it backwards. They said that when a metal like mercury was heated, phlogiston flew out of it, but Lavoisier had shown that on the contrary, air had gone into it. 8 cubic inches of air, to be exact. And that, Lavoisier concluded, was why the metal gained weight when it was heated, not because phlogiston weighed less than 0. But what kind of air was it? Was it air or something in the air? Lavoisier had to know. He gathered the red specks that had formed on the mercury and heated them strongly, gathering the gas that they gave off. What was it? Priestley's dephlogisticated air. 8 cubic inches of it. But contrary to Priestley and the phlogistians, Lavoisier had just shown that heated metal did not give off phlogiston. Instead, it gained a gas from the air. Neither phlogiston nor dephlogisticated air were real. The dephlogisticated air must be something else. Lavoisier named it oxygen, from the Greek words meaning acid generator, because Lavoisier thought all acids included oxygen. Lavoisier now re-explained everything the right way. When a candle burns under a glass jar, when a candle burning under a glass jar snuffed out, it was not because the candle had finally filled the air in the jar with phlogiston, but because the candle had used up all the oxygen from the air. When a mouse put under a glass jar soon died, Lavoisier argued that was simply because the mouse, like the candle, needed oxygen. Indeed, argued Lavoisier, combustion, burning, and respiration, breathing, Both require oxygen because respiration is a kind of combustion. Animal bodies need oxygen to burn the food and create heat for their bodies. But Lavagier's revolution had just begun. He now turned to Cavendish's experiments, which were supposed to prove that inflammable air had dephlogisticated air produce water and set these aright too. He put together some oxygen, dephlogisticated air, and some of Cavendish's inflammable air and sparked them water, just as Cavendish had reported. But Cavendish had thought that the inflammable air was actually water plus phlogiston. Nonsense, replied Lavager. Phlogiston does not exist. Inflammable air must be an element itself. Lavager named it hydrogen, which comes from the Greek word means water generator. And so, after centuries and centuries, going all the way back to Thales, Lavager had finally seen clearly that water was not an element at all, but was made out of two elements, two fundamental things, oxygen and hydrogen. And the air, it was not an element either, but made up of at least two elements. Remember the 50 cubic inches of air in the first experiment? Lavager had shown that there were 8 cubic inches of oxygen in it. That meant, argued Lavager, that common air, which everyone had thought was an element, was made up of about 16% oxygen. Later Lavager calculated to be about 20% oxygen, which is close to the real figure of 20.948%. What kind of air, what kind of gas was the 42 cubic inches left over? Lavager tested it. A candle would not burn in it, a mouse would not live in it. He called it azote, which means no life. A bit later, a man named Jean Chaptal gave it the name that we call it today, nitrogen. But whether it was called azote or nitrogen, the important thing was that Lavager identified it as an element that makes up air. Interestingly enough, Lavager is often not credited with the discovery of nitrogen. Instead, the credit is given to Daniel Rutherford. Well, it is true that Mr. Rutherford was the first to isolate nitrogen, although we must add that Priestley and Cavendish had also done so about the same time. Rutherford did not identify it correctly. He thought it was air saturated with phlogiston. But as we have seen today, Lavager proved that phlogiston did not exist. Mr. Lavager and his wife Mary were so confident and so excited by Lavager's proof that they staged a celebration. When Marie, acting as a priestess, burned the writings of the phlogiston's first proponents, Becher and Chaptal, on an altar. Lavager was, we imagine, sure to point out that burning paper was using oxygen and not giving off phlogiston, unless we consider the burning of the theory the final sending off of phlogiston. But he was still not finished with his revolution. Lavager was the first to make clear a very important principle in chemistry, one which is used in the above experiments. It has come to be called the conservation of mass. It is a very simple but very profound principle, for it allows chemistry to keep a balance sheet. One may take it for granted, Lavager proclaimed grandly, that in every reaction there is an equal quality of matter before and after the operation. If the 50 cubic inches of air in which mercury is heated drops down to 42 inches, then the 8 cubic inches of oxygen must still be somewhere. It does not disappear, but changes places. It is no longer in the air, but in the mercury. The mercury has gained the 8 cubic inches, not in size, but in weight, and weight as much as the original mercury plus 8 cubic inches of oxygen. There is still the same amount of matter. It is just in a different form. It is easy to see how revolutionary were Lavager's contributions, but even with all these wonderful things, Lavager had yet other changes in mind. All right, see you next time. Bye.